Today we are going to look at a more illustrative problem. It's a sort of a practical problem. It's still a toy problem, but it will give you a sense of how everything works. So today we will look at an illustrative problem. And the problem, let's try to first develop intuition for it. So we have n particles. These could be anything, any n objects, okay? These particles are distinguishable. These particles are independent. They do not really talk to each other. They do not interact with each other. And they can exist in one of two states with energy 0 or epsilon. Okay, so for example, you could all be n particles, you're distinguishable from each other, and the two states could be you sitting down or you standing, right? So if you're sitting down, the energy is 0. If you're standing, the energy is epsilon. You are, however, distinguishable from each other, and you are in reality, you are interacting with each other. If all of you are standing up, maybe that other person also wants to stand up, right? It's like, why is everyone standing up? But what we are assuming here is, no, it's independent. Whatever you do is completely independent. Distinguishable. Have you seen Squid Game, any of you? Are the Squid Game participants distinguishable or indistinguishable? They have a number though. So distinguishes, they always say participant number 144 eliminated, right? It's that particular person who is eliminated, right? So think of it that way. So I can write down Squid Game. So, and what we want to do is to model this system and figure out at any given temperature, what will be the average energy of these n particles? What are they going to do? All sorts of thermodynamics, okay? So let's develop intuition for it. And Max, I'm gonna ask you this. At I just remembered this morning, I haven't asked you a question yet. At very low temperature, let me draw a box so we can visualize it a bit better. So let me draw a box like this. And what we are going to do is to call this as particle number 1, particle number 2, particle number 3, particle number 4, ... particle number n, okay? And this corresponds to epsilon energy. One second. Energy 0, and this is energy epsilon. So every particle can be either here or here, right? It cannot be in both at the same time. So Max, my question for you is, at very low temperature, at temperature is equal to 0, what do you expect the particles to do? Every particle should be in the ground state, right? At 0 temperature, that's correct, but I have one more question for you. That was the easy one. At 0 temperature, we expect the average energy of this system to be 0, right? Okay, Max, how about infinite temperature? Very, very high temperature. What do you expect then? And forget StatMech, just use your intuition. Who thinks everyone should be in epsilon? Who thinks everyone? It might be more complicated than that. Go ahead.
I just think it should be an epsilon. That's
You think it should be an epsilon? Really? Does everyone think that? Go ahead. Let's not worry about it. We are thinking about very basic, in the pre-entropy world, just intuitively. At very high temperature, should everything be in epsilon? At n epsilon over 2.
I have an answer.
Yeah, go ahead.
Epsilon over 2.
Yeah, so Uni also said the same thing. So Uni, what's your argument? At very high temperature, why should this be n epsilon over 2?
At t
tends to infinity is equals to 1. So have equal probability of being at energy 0.
Yeah, so you're thinking about it mathematically. We can also think about it intuitively. The idea being that at very, very high temperature, the difference between 0 and epsilon is very minimal. It doesn't matter. It's like if this room was extremely hot, maybe you're sitting, maybe you're standing up, you're just so much miserable about the heat that it does not matter, right? So that's why it's going to be on an average epsilon over 2. Okay, so intuitively we expect this to be true. What we are going to do next today is to actually derive an expression. So these are the two limits, at 0 temperature, at infinite temperature. But then the question is, what happens at finite temperature? How does it change? How does it go from 0 to n epsilon by 2? Is it just some monotonic behavior, or is some complicated behavior that goes on? Does entropy play a role? What goes on? So we will calculate average energy of the system as function of temperature using, and we will do it through both ensembles. We will first do it using NVE ensemble, and then we will do it using NVT ensemble, both of them. Volume does not really play a role here, so we are going to ignore it. So in a sense, we are working with NE ensemble and NT ensemble, right? We are not talking about volume, even though it is NVE and NVT, and N is constant in both cases. So let's work with this. Approach 1, which is NVE ensemble. Okay. NVE ensemble, in both cases, let's first think about the microstate of the system. How do we define the microstate of the system? So the box that I drew earlier, I can again draw a box like that over here. And let's say my particles are distributed. In certain microstate, I have particle number 1 in energy epsilon, particle number 2 in energy 0, particle number 3 in energy 0, so on and so forth, right? If I enumerate exactly where every particle is, that is the full microstate of the system, right? Earlier you studied microstate is phase space, but here we are not talking about velocity or anything like that. It's a simple model system. So here, this uniquely tells you the microstate. You could have another microstate that looks like this, where every particle is in ground state and the fifth one is in excited state, right? So these are all different microstates. Mathematically, we can write down this microstate in the following binary number format. If the first particle is in excited state, this is particle number 1, then we call it as 1. If the second particle is in ground state, we call it as 0. So given whether a particle is in excited state, we call it 1. If it's in ground state, we call it 0. Okay, so the first one will look like 1, 0, 0, 1, 1, 1, right? So if you have a long binary number, which tells me the complete definition of the microstate. This one, what will be the microstate? Right? 0, 0, 0, 0, 1. So, and we could keep writing down this for n particles, depending on how many particles do we have. So, how many microstates can we have then? Is everyone agreeing with that? Each of their independent. The independent is importance there, right? So number of microstates, each of them can exist in two different ways. So the number of microstates is 2 to the power n. But that is a very large number. That does not account for what energy do these microstates have, right? Out of these 2 to the power n microstates, there is one little microstate. If I ask you about the number of microstates where energy is equal to 0, that's one of these 2 to the power n. Right? Do you agree with that? That there is only one ground state? The only microstate where the energy is 0 is the one where the whole binary number is 0, right? So the number of microstates where the energy is equal to 0 is equal to 1. The number of microstates where energy is equal to n multiplied by epsilon, everything is excited. How many microstates do we have in this configuration? Again, 1. Each of them have to be excited, right? So this one will correspond to 1, 1, 1, 1, 1, right? The binary number that looks like this. If I ask you omega n e is equal to epsilon. Now you have to think of it. How many such microstates will I have where n minus 1 particles are in ground state and 1 particle is excited? N. Does everyone agree with that? Fatima, is that clear? Huh? Because how will this look like? This will look like either the first one is excited, 1 0 0 0 0, or the second one is excited, or the third one is excited, so on and so forth, right? So you have n of those. Now it gets complicated as you get to omega n, not epsilon, not 0, not n epsilon. These three are easy. Now let's talk about the general case where we are thinking about some m epsilon, okay? Where m is some number which is smallest equal to 0 and highest equal to 1. What is this going to be? This, huh?
Oh, you were asking.
Yeah, anyone?
N factorial divided by n factorial times n minus 1 factorial.
Yeah, so this is the number of ways in which you can choose m numbers. So what does this mean? This means if you have 5 particles, 2 of them have to be excited, right? So let's think about the simple case where you had 4 particles, okay? For example, you have 4 particles and you are looking at 2 epsilon. So how many ways could you do it? You could do it, well, 0 0 1 1, 0 0, sorry, 0 0 1 1, 0 1 0 1, 1 0 0 1, right? Or you could do, well, you can write it down. There will be how many in this case? In this case, it will be 4 factorial divided by 2 factorial divided by 2 factorial. So that is a total 6 possibilities, right? Did I get it right? How much is 4 choose 2?
6.
Is it 2 into 3 into 4 divided by 2 divided by 2? It's 6, right? So you have 6 ways. And this is the number of combinations you can have. If the particles were distinguishable, this answer would have changed. Since they are indistinguishable, we can use this formula for combinations. So let me go to next page and write down this formula. So we have omega, number of microstates where energy is equal to m epsilon is equal to n choose m. That is going to be n factorial by m factorial by n minus m factorial. Is there a question?
If they're distinguishable, shouldn't it be a permutation?
No. Because permutation means which order did you, even though they are distinguishable, why do you think it should be a permutation?
I
Usually you associate distinguishable with permutation, right? So let's think about it. The reason it won't be a permutation is because it does not matter in which order did you excite them. The fact that they're excited is all that matters. So, like let's consider Max, Rachel, Julia, and Rael. And I say out of U4, 2 are in ground state, 2 are in excited state. So it does not matter whether I say Max, Rachel are in ground state, Julia, Rael are in excited state. Or I say Rachel, Max are in excited state and Julia, Rael are in ground state, something like that. Sorry, as long as you have the right number of people in the group, it does not matter who you say first, right? That's why it's going to be combination. Good. These things can be confusing, so it's good to check always what's going on. So, okay. Now we know we want to replace M because we are interested in understanding what happens for the energy E, right? So M is related to E by epsilon, right? What is M here? M is number of particles in excited state, right? Great. So let's work with it. So omega n E is equal to m epsilon is going to be n factorial by E by epsilon factorial by n minus E by epsilon factorial. So let me say this is equation number 1, and let's say this is equation number 2, and we will see which one do we need to work with. So first and foremost, in StatMech, it's very rare that we have to deal with omega. What we need to deal with is log of omega, right? Log of omega is what, or log of partition function. That is what contains information about thermodynamics, right? So let's take log of both sides, because that's what we are probably going to work with. So log of omega, let's work with equation 1. Keep the m. So log of omega is log of n factorial minus log of m factorial minus log of n minus m factorial. Now, so far everything is exact. We haven't made any assumptions. Now we are going to make a crucial assumption. We will assume that n is much more than m, which is much more than 1. What does this mean? It means you are sort of in the thermodynamic limit. You have n is a very, very large number. And the number of particles you excite, that is also a very large number. However, it is much smaller than n. Both of these things are important. Otherwise, we won't be able to make progress in this problem. Okay. Once we have this, we can go to equation 3 and use an approximation which no one mentioned in the first class, but shows up in StatMech all the time, which is approximating log of n factorial. So Stirling formula says that log of n factorial is equal to n log n minus n. It's approximate, okay? It's a very quick way of calculating things. You can kind of see why it is correct. You know that what is ln of ln? You can see, for example, if I did not have this term over here, then clearly this is bigger than ln of n factorial, right? Because what is ln of n factorial? ln of n factorial is ln of 1 multiplied by 2 multiplied by n. And what is this thing? This thing is ln of n multiplied by n multiplied by n times, right? So you can see that this thing is clearly larger than this thing. So the n is a correction. And you can write down what is known as the Euler-Maclaurin formula for this one, because this correction is a bit too harsh. It overcompensates. So you can add a second term, you can do Taylor series, you can do all sorts of funky things. But what we are going to work with is, this is a formula you should remember. ln n factorial, I should erase the cross so you don't get confused later. So I don't have to write it again also. So ln n factorial is approximately n ln n log n minus n. So use this for, we can, why did we write down this approximation? This, since n is much larger, and oh, by the way, I forgot to say something obvious. This becomes true as n becomes much larger than 1. If you do it for 2 factorial, this is not going to be true. Okay, you can try yourself. What is 2 factorial? That is 2. What is natural log of 2? I don't know, it's a number smaller than 1, right? It's around 0.7 or something. So you will see it becomes a negative number, actually. It will be wrong. So you have to make n very, very large for this to be true. So in this case, this is much larger than 1. We assume that to be the case. We also assume that m is much larger than 1. And furthermore, we assume that n is much larger than m, right? Therefore, n minus m is also much larger than 1. So we can apply Stirling formula for all 3 things separately. So let's do that. Equation 3 gives ln omega is approximately n ln n minus n minus m ln m plus m minus n minus m ln n minus m plus n minus m. Okay, just Stirling's formula applied for all 3 things separately. Now something nice happens. minus m and plus m cancel, minus n and plus n cancel. What are we left with? We are left with ln omega is approximately n ln n minus m ln m minus n minus m ln n minus m. Okay? So that's ln omega. That's what is this? This is approximately the number of microstates, the log of the number of microstates for any value of the energy. It's not going to be true if your m is all close to n. If you get really close to n, and we will probably be okay because we expect m to become n over 2, right? At very high temperature, we expect half of the things will be excited, right? So we are going to push it that if n is a very large number, we will push m to become something like half of n. So if n is 40 billion, then m is going to be 20 billion. So the difference is still a number which is much larger. 40 billion is much larger than 20 billion, that type of idea here. So let's write this equation. Let's call it equation number 4, and we will work with it on the next page. So what we need now is thermodynamics. From ln omega, we know we can get entropy, right? Because we are working in microchemical ensemble. So S is equal to Kb ln omega. Let's go one step further. Let's try to get the temperature from ln omega. And now you should remember this formula for microchemical ensemble, or try to remember it, that beta is equal to partial derivative of ln omega with respect to energy. In this case, at constant n. And volume also, but we don't have any volume, right? So if you want to be a stickler, you can write down constant n and v, right? So notice that equation 4 is ln omega approximately n ln n minus m ln m minus n minus m ln n minus m. Okay. So to get beta, we have to differentiate this thing with respect to energy at constant n and volume. So when we differentiate it, what's going to happen to this thing? It won't matter because we are doing it at constant n, right? It will be 0. This one and this one will play a role. But it does not have E over here, it has M over here. What is the relation between M and E? M is equal to energy divided by epsilon, which is the number of particles which are in excited state. So, well, now it's going to be just glorious algebra, nothing profound. So let's suffer through it. So what we will do is to write down beta is equal to partial ln omega by partial E at constant n. So that becomes partial ln omega by partial m epsilon at constant n, right? Because energy is equal to m epsilon. This epsilon is a constant number, right? What is the value of the ground state? Excited state relative to that, right? So epsilon can go outside the partial derivative. So this becomes 1 over epsilon partial ln omega by partial m at constant n. This is beta. Let's call this equation number 5. And we have ln omega written down in equation number 4. So all we need to do is to go to equation number 4 and differentiate it with respect to m, right? And then we will get going. So therefore, use 5 in 4. What do we get? We get partial ln omega by partial m is going to be, first we differentiate this one. So that will be minus m 1 over m, and it's a product rule, minus ln m, then minus n minus m divided by 1 over n minus m, but this time we will have a minus 1 sign also. And I know I'm going fast through this algebra. If you are in this course, hopefully this type of algebra should be trivial to you. If not, then you need to practice a lot. Okay, so all I have done is to take functions like m log m and do product rule on it, right? I differentiate m keeping ln m constant. I differentiate ln m keeping m constant, right? And then I be very, very careful with signs. So once I get this, I can, this term becomes -1. Then I get minus ln m. This term becomes +1. And then I get plus ln n minus m. -1 plus 1 cancel, or I get partial ln omega by partial m is equal to ln of n minus omega by m. Or partial ln omega by partial m is equal to ln of n by m minus 1. And now use equation 6. Equation 6 says that beta, the inverse temperature, is 1 over epsilon partial ln omega by partial m. So that is going to be 1 over epsilon ln of n by m minus 1. Let's call this equation number 6. I will pause here for a bit. Any questions about this? If I took a snapshot of this, if you took a snapshot of this and went to one of your family members, and let's assume they don't have a PhD. If they have the PhD in sciences, then my test is not going to work. And you told them this is chemistry, you'll be like, get out of here. What does this have to do with chemistry? But that's the equivalent of many of you who plays music here. Julia plays music. What do you play? The piano. It's like Julia showing me sheet music and saying this is music. I'm like, get out of here. That's not music, right? Sheet music does not look like music unless yes. So this type of algebra is the equivalent of sheet music for chemistry, right? This is what allows us to be very precise in what we are trying to communicate. And science is about being precise, right? We cannot just make, if we had to make hand-wavy arguments, we would just use S is equal to K log omega and be done, as we know, but we know it's not true, depending on what the control variables you have and everything, right? So for those of you who don't like math as much as I do, this can all seem painful. But it's the sheet music, right? And that's why you have to really become comfortable with it. Otherwise, nothing will happen. And you can get there. It's not impossible. And once you work through this, as we will see in a moment, the answers you get out of it can be quite intuitive, which is amazing. So that's
I have a question.
Yeah, go ahead. Go ahead, Noah.
Sorry. I know we had to assume that n is much greater than m and m is much greater than 1. But I noticed that if you were to plug in m equals n, you would end up with negative infinite temperature, which is, as far as I'm aware, correct for if all of the
But why are you putting capital N is equal to small m?
Or no, I'm just saying, like, if you were to plug in,
but I won't let you.
Value, I know that contradicts the assumption that
I won't let you. Problem
but
solved.
But it still gives minus infinity temperature.
I wouldn't trust you.
Okay.
You're breaking my hypothesis. I told you, don't do this.
Okay.
You lose. You have more negative price now.
No.
Yes. You can do it, and maybe you get a meaningful result, maybe you don't, but that's not the assumption we are working. Okay, so be careful. Okay, boring answer, but that's what it is. So what do we have? We had beta, the inverse temperature, is equal to 1 over epsilon ln n by m minus 1. Dimensionality wise, it makes sense. Beta is the unit of 1 over kT, right? 1 over energy. And on the right side, you have 1 over energy multiplied by log. Log does not have dimension, right? So we haven't screwed up our dimensions. So now we can get beta epsilon is equal to ln by n by m, ln of n by m minus 1, or n by m minus 1 is equal to e to the power beta epsilon, or 1 plus e to the power beta epsilon is equal to n by m, or, and now it's starting to get interesting, m by n is equal to 1 over 1 plus e to the power beta epsilon. Does this have a physical significance? This is the fraction of particles which are in excited state, right? This is fraction of particles in excited states. And we also know that energy is equal to m multiplied by epsilon, right? If m is the fraction of, if m is the number of particles in excited state, then energy is going to be m multiplied by epsilon, right? So we can multiply this in the above equation and get E is equal to n epsilon divided by 1 plus e to the power beta epsilon. And suddenly we have an expression for the energy at any temperature. Let's check whether it follows Max's intuition. As T tends to 0, beta tends to infinity, right? If beta tends to infinity, in the denominator, e to the power beta epsilon dominates. What's the 1 going to do, right? The denominator, 1 plus e to the power beta epsilon tends to infinity, right? And the whole thing tends to 0. So we recover the ground state, correct? That's fine. Now let's do the harder one. As T tends to infinity, beta tends to 0. 1 plus e to the power beta epsilon tends to how much? Negative rise. 1 plus e to the power 0. 2. That's the whole difference, right? So E tends to n epsilon by 2. So it recovers the intuitive limit that we had. This form is also very interesting. This type of function where you have 1 plus denominator of 1 plus e to the power energy is going to show up a lot later in the context of Fermi-Dirac statistics and Bose-Einstein statistics. Sometimes it will have a 1 plus e to the power beta epsilon. Sometimes it will have a 1 minus e to the power beta epsilon. And the phenomenon of Bose-Einstein condensation, for which Nobel Prize was given in 1996, is related to the fact that sometimes the denominator can go to 0 and funky things can happen, and all particles can condense in one state and things like that. We will be doing all of this later. For now, you don't have to worry about it, but just keep in mind that this form of 1 by 1 plus e to the power something, or 1 by 1 minus e to the power something shows up in StatMech, not just classical StatMech, but quantum StatMech quite a lot. Oh, this is interesting. Noah, the question you just asked me in my notes, which is a printout from, I cannot really show it to you, from 2 years ago, someone asked me exactly the same question. And I have drawn my face over here because I got very grumpy, you can see. Someone asked me, what happens if m is equal to n? And I got beta tends to minus infinity. So I think it was Vedant. Does anyone know Vedant? He's in biophysics. He asked me that question. Yeah, and I probably had the same answer, like you cannot do it. Okay, there is a practice problem for you here. Let's number this as equation number 7 and equation number 8. I want you to plot equation 8 versus beta and develop intuition for how it looks like, or versus temperature. Once do it versus beta and then do it versus temperature and play with it and see whether it makes sense or not. Okay, any questions about all of this? So we did this using microcanonical ensemble. Now we are going to do the same problem using canonical ensemble. And we will get the same answer as we should in very high n limit. They won't be the same in finite n limit because we won't be able to do this for the finite n limit in microcanonical. Why not? Because we use Stirling's formula, right? We use the approximation for ln of n factorial, which is valid only for very, very large n. So in a very sneaky manner, we have already assumed thermodynamic limit in this. In a canonical ensemble, however, you will get an answer which is valid even for small n. And that's kind of cool. And all ensembles become the same at very, very high temperature, okay? So note that approach 1 inherently assume thermo D limit when we said n more than 1. Okay, now we work with canonical ensemble. Canonical ensemble, which is our approach 2, and we will show that it ends up giving similar answer or the same answer. And the math here is going to be slightly different, and there is something interesting that happens here, and we will be using the fact that the particles are independent. So for microcanonical ensemble, we wrote down omega of NVE, right? And that was a combination problem. For canonical ensemble, our point, what we need to calculate is the canonical partition function, Q of NVT, right? So what is Q of NVT? What is the definition of Q of NVT? Go to every microstate and calculate e to the power minus beta energy of that microstate, right? So today, possibly for the first time in your life, you're going to see a very bizarre summation where you have a summation and you have an exponential, and inside the exponential, there is another summation. And that's going to be fun. Why is that going to happen? Because remember that we wrote down our microstate definition as numbers that look like 0, 0, 0, 1, 1, 1, 1, 1. If you're a Futurama fan like me, that's how Bender sounds every once in a while. He just goes on saying long binary numbers. Anyway, is there any Futurama fan here? Huh? There you go. You remember where it was written? On his ass. And it was very microscopic. And he was like, oh, I have some number written here. And he goes reading it. And he just keeps on saying a long binary number. And when he stops, he has discovered the code to time travel.
It is fun also in that episode that it's all like it wraps into itself.
It's crazy.
It's self-contained. So
it is self-contained. He goes out and like, yeah. He kills Hitler in one round and then comes back and does something else. Anyway, we are going. It's a great show. You should watch it. Additional watching for 687 is Futurama. Okay, good. So that's our microstate definition. I'm going to define a variable n, which says what happens to particle number. So n1 is equal to 0 or 1, depending on whether particle number 1 is in ground state or excited state. Okay, so in this case, n1 is equal to 0, n2 is equal to 0, n3 is equal to 1, n4 is equal to 1, ... n capital N is equal to 0. Okay, so I have just defined a number, nj is equal to 0 if j is in ground state, and j is equal to 1 if j is in excited state. Why do I need to do this? The reason I need to do this is because this allows me to write down the energy E nu for any given microstate. So now, in this particular case, if I want, so let's consider this binary number I have over here. What is the energy, the total energy of the system for this binary number? For the first particle, how much energy do we have? 0. It's in ground state, right? So for the first particle, we have energy 0. For the second particle, we have energy 0. For the third particle, we have energy 1, then 1 plus 1 plus ... right? What we are doing here is to write it in a slightly sneaky manner. We are writing it as, well, this is 0, but 0 is the same as 0 multiplied by epsilon, right? This is the same as 0 multiplied by epsilon. This is the same as 1 multiplied by epsilon, 1 multiplied by epsilon. And now, given the numbers that we introduce, these numbers are, you can call it sort of an occupation number, is which state is the particle occupying. Occupation, sorry, not occupation state, but occupation number, okay? So this thing is now going to be, notice that for this particular microstate, N1 was 0, right? So this is nothing but N1 multiplied by epsilon. This is N2 multiplied by epsilon. This is N3 multiplied by epsilon. Or for any microstate, we can write down that the energy E nu is going to every particle from particle 1 to n, looking at its occupation number, right? Nj says, are you in ground state? Are you in excited state, right? If you're in ground state, Nj is equal to 0. If you're in excited state, Nj is equal to 1. Is that okay? What do you think, Didi? Is that fine with you?
I zoned out for like 2 seconds, I don't know.
Zoned out. We all zone out, it's okay. Are you back now?
Yeah,
Okay, are you okay with this?
wait, I'm done again.
He's back. Okay. So what we are doing here is to go to every particle. Let's go to particle number 1. And if the particle number 1 is in ground state, then N1 is equal to 0. If the particle number 1 is in excited state, then N1 is equal to 1, right? So if it is in ground state, N1 multiplied by epsilon will be 0. If it is in excited state, N1 multiplied by epsilon will be epsilon, right? And that's what we are doing for every particle. And these are independent particles, so the energy is going to be a sum of them. In reality, things are not independent. You will have products of NJs and life will be super complicated. Okay, so this is our thing. And by the way, if you zone out in a class, it's totally okay to interrupt me and say, you sent me to sleep. Can you repeat again? It's better than you losing track. Okay, it's our pace will keep picking up. So it's important that you stop me if I go too fast. So this is the energy of the system. Okay, it looks abstract, but really isn't abstract. You're going to every particle and seeing, is it in ground state or in an excited state? If it's in the ground state, you have introduced a variable which accounts for this, and that variable is the n variable. Okay, so let's call this, let's write down the partition function Q as equation 8, and let's call this as equation 9. So now we have to put equation 9 inside equation 8, and this is what I referred to earlier. You already had a summation, and now this thing is going to be a summation too. So it's like mega summation. Okay, so put 9 in 8. What do we get? Q of NVT is equal to summation over all microstates of e to the power minus beta summation j is equal to 1 to n for every particle nj epsilon j. That's my, at this point, you would give up and go back to microcanonical partition function. Be like, there is no way I can do anything with it. But it simplifies nicely. Let's work through it. So first thing I'm going to do is to think about what does a microstate mean. Microstate means whether a given particle is in ground state or excited state, right? So a microstate is a set of binary numbers, right? So for defining a microstate, you're going to N1 and looking whether it is 0 or 1. You're going to N2, you're looking whether it is 0 or 1. You're going to N3, you're looking whether it is 0 or 1. Okay, that's the definition of my microstate. For each such microstate, and you have such 2 to the power n such microstates, you go and write down e to the power minus beta, and let's spread out this summation that we had. Okay, so this is going to be n1 epsilon 1 plus n2 epsilon 2 plus n epsilon n. Okay, one super nice thing about e to the power anything is that e to the power x plus y is the same as e to the power x multiplied by e to the power y, right? So now I can do something very interesting. I can write down this summation as n1 is equal to 0 or 1, n2 is equal to 0 or 1, dot, 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 e to the power minus beta n1 epsilon 1, e to the power minus beta n2 epsilon 2, e to the power minus beta n epsilon n. Okay, I've just split out the exponential. Then I realize that this summation that I have over here is not just one summation, it's an n-dimensional summation, right? We're doing it for every particular particle. And N1 summation corresponds to only this exponential. N2 summation corresponds to only this exponential. So I can do something else which is very interesting, and I can write it down as, so let me first write down the full summation. I'm doing N1 is equal to 0 to 1, N2 is equal to 0 to 1, and N is equal to 0 to 1, e to the power minus beta N1 epsilon 1, e to the power minus beta N2 epsilon 2, e to the power minus beta Nn epsilon n. Okay? So the point I'm making here is, as you change the value of n superscript n, n subscript capital N, the only thing that is going to be affected is this one. As you change the value of N1, the only thing that is going to be affected is this one. As you change the value of N2, the only thing that is going to be affected is this one. So suddenly we can do something amazing, which is write it down as summation. It's like when you do multivariable calculus or multivariable integral, and you have integral dx dy, and the function is x multiplied by y. Well, it's just integral dx multiplied by integral dy, right? However, it was xy plus yx squared, then you're screwed. And you have to think more carefully, right? Or it was x multiplied by cosine of y, then you cannot do that. Then you have to do the full thing. So this is going to be n1 0 to 1, e to the power minus beta N1 epsilon 1, N2 0 to 1, e to the power minus, sorry, why did I write everyone's zoned out? Did everyone zone out? I did something very funny here. Why on earth did epsilon get a subscript? There is no subscript in epsilon, right? Every particle has the same excited state value. So this epsilon j that I have been dragging is a crime. You could imagine a very complicated problem where different particles have different excited state values, but not here, right? It's very simple. Yeah, go ahead.
Okay, I assume you added a subscript because I assume that if it was the same epsilon, it would be pulled out of the sum.
Yeah.
Can you pull it out of the
That's
sum?
what we are going to do now.
Cool.
It will look amazing. Life will suddenly become beautiful. So minus N2 epsilon. But before we do that, we are going to realize something else, hopefully, is that, so what do we have now? We have a product of n things. Let's write down the first one explicitly. It's a simple summation, right? N1 can only go from 0 to 1. It's a summation with two terms, so you can just write it down explicitly. What will this one be? When N1 is equal to 0, what is the value of this thing? E to the power 0, right? 1. When N1 is equal to 1, what is the value of this thing? Correct? Let's go over here. When N2 is equal to 0, what is the value of this thing? 1. When N2 is equal to 1, what is the value of this thing? You see something appearing? They are all the same. Why is that not surprising? Because these are independent particles which do the same thing. So 1 plus e to the power minus beta epsilon. And suddenly we get a glorious expression that Q of NVT is 1 plus e to the power minus beta epsilon to the power n. That's awesome. Let's see one thing. Okay, so we have our partition function now, and we are ready to do thermodynamics. So we have Q of NVT is equal to 1 plus e to the power minus beta epsilon to the power n. Let me write down this expression here again. Q of NVT is equal to 1 plus e to the power minus beta epsilon to the power n. This expression is also very important because what does it show you? It shows you that the n particle Q is product of n one particle Q. That's what we saw, right? So if you were trying to be very lazy, you would not have done all of this business. You would have said, yes, I know we have n particles, but I don't care. I'm just going to calculate the partition function for one particle and take it to the power n. And you would have got the same answer. That you could have written this right away, right? You would have said Q is equal to summation e to the power minus beta e nu for microstate. And let's imagine in your world, there is only, I see Vivian smiling. So I'm going to assume Vivian as my particle. Vivian in ground state, Vivian in excited state, okay? So in that case, what is it going to be? When Vivian, so in this case, this is n Vivian from 0 to 1, right? E to the power minus beta n Vivian epsilon. And that is 1 plus e to the power minus beta epsilon. And then I say, well, every particle is the same. They are distinguishable, but their energetics is the same, right? So I can just take to the power n. Therefore, Q of the n particle system is Q of the one particle system to the power n. Notice here, I assumed them to be distinguishable. If they were indistinguishable, I would have to correct. I would have to put here a 1 over n factorial. And later we will revisit why this approximation works only for large n. You have a problem if you use this for small n. There will be a homework problem sooner or later where you will get confused about this one and hopefully get clarity after that. Okay, so this also shows why we call this thing Q as a partition function, right? It partitions between different things of the system, right? It's a product of different things. So let's stick with our Q now. So we have Q is equal to 1 plus e to the power minus beta epsilon to the power n. What is the connection between Q and thermodynamics? It's the Helmholtz free energy, right? So A minus beta A is equal to ln of Q. What is ln of Q? That is n ln 1 plus e to the power minus beta epsilon. We have our Helmholtz free energy for this. For canonical partition function, we also derived the value of the average energy in class. It was something related to the log of the partition function differentiated. Anyone remembers what was the expression? It was partial ln Q by partial beta at constant n. Okay, so we can do that. Once we do that, you easily get this is n epsilon by 1 plus e to the power beta epsilon. And let's call this equation 11. Equation 11 is the same as equation 8. For microcanonical, we got energy is equal to n epsilon by 1 plus e to the power beta epsilon. And here we got average energy is equal to n epsilon plus 1 plus e to the power beta epsilon. This is same as NVE answer in equation 8. Notice, of course, that in this case, we are talking about the average of the energy because we are working with a canonical ensemble, so energy can fluctuate. In microcanonical ensemble, we did not have average of energy, right? There was no fluctuation because we threw energy. So both ensembles gave us the same answer. And while it might appear to you that we did not have to invoke thermodynamic limit, we did not invoke thermodynamic limit for the canonical partition function. For the microcanonical case, we did invoke thermodynamic limit because we used Stirling's formula. Any questions about this? That's all I have for today.
Wait, I have a question.
Yeah, go ahead.
So if we don't need to invoke this thermodynamic limit to get this expression, meaning we don't need to strictly assume that n is very large, doesn't that mean that if you like plugged in the m equals n thing with the microcanonical, wouldn't that make it okay? Or never mind, I don't want negative prizes.
You really want negative prizes. I'm sure you will get funky things, but in this case, you can actually work with m equal to n. This allows you to do that. You will get an answer here And you might find that macrocanonical actually does better than what you thought. But I would not put my money on it. For this problem, the lesson is if you want an answer for finite n for any value of m, the way to proceed is the canonical ensemble. Macrocanonical ensemble can also be used, but the answer won't be valid in all regimes. And Noah has really motivated me to set up this as a problem for you to play with at some point. We will do that. Good. Okay, see you next week.